Hello, my name is Dibakar Dhara. I belong to Chemistry Department of IIT Kharagpur, and I will be teaching you the unit on thermodynamics. So, if in this lecture, probably in the first first 2 hours of this unit, we will talk about essential concept and definitions, and then heat will talk about introduce the concept of heat, work energy and internal energy, and then we will talk about first law of thermodynamics, and then we will go in the calculation of work heat in different processes for an ideal gas, and we will talk about enthalpy and heat capacity, and we will then talk about determination of experimental determination of del U and del H. We will come to those terms in a minute. So, this is just a basic outline of the first 2 lectures, and obviously, we will move to other lectures. I will show you the content of the other lectures when time comes. Now, let us begin with some pictures. This is now it is a winter time here, and you can see people are trying to get some heat, just burning some leaves here. So, what is happening here is the chemical energy stored in these leaves, they are basically reacting with oxygen and getting burned, and in that process it is producing some heat, and of course, some light also will be there. So, in this case the chemical energy is getting converted into heat energy and light energy. In this picture you see cars are running, and most of the cars still run on fuel, petroleum or diesel, and what happened in this case, the petrol or diesel get burned in the engine, and as a result this mechanical energy, the car starts running. So, this is the example where chemical energy is getting converted into mechanical energy, and of course, you can argue that there are cars nowadays which runs on battery. So, this is just a picture of one battery, and so what happens battery basically because of the chemical reactions in the battery, electrons are pumped in the outside circuit. So, as a result you get electricity. So, in this case you get you are basically getting electrical energy from chemical energy. If it is a rechargeable battery, then you can charge it again by applying electrical energy from outside and getting back the chemical reaction. So, basically while charging you are converting electrical energy to chemical energy, and while discharging you are basically converting the chemical energy into electrical energy. So, these basically are examples to show you or convince you that probably you know already all these things, that energy are interconvertible. So, you can actually convert one form of energy into the other form, and thermodynamics is the part of science which deals with the interconversion of energy, and in broad sense it deals with macroscopic systems, and in this unit we will talk about only the systems which are at equilibrium and the properties of systems which are at equilibrium, which means we will deal with only equilibrium properties of the systems in this unit. Now, thermodynamics was first formulated by physicists and engineers when dealing with the efficiency of steam engines, but it is of extreme importance or immense help for both chemist and biologist. While on one hand it basically explain or deals with the energy output from a chemical reaction, on the other hand it basically forms the basically helps in explaining or answering the questions which are center or at the heart of biological sciences, like for example, how the energy gets transmitted through the biological cells, or how the large macromolecules get assembled within a small volume of cell. So, these are the main questions the biological science poses also had to be answered from the knowledge of thermodynamics. So, basically you know that thermodynamics is a very important subject and we should learn thermodynamics. So, if we just write once more that and in this unit, as I said, we will be dealing with the equilibrium systems. And will not consider systems having very few molecules. We will be talking about systems which have great number of or many molecules. So, this thermodynamics does not apply for systems which has very few molecules, but it is applied or applicable only on systems which have large number of molecules. So, if we just write, we will talk about systems containing large number of molecules. So, on that we are talking about a macroscopic system, not a microscopic systems. We are talking about macroscopic systems. Now, we have used these terms quite a few times or talked about these terms systems. Now, obviously, what is systems or what is a system? System is the part of the universe which is of our interest. Our interest means which is of our interest in that moment. For example, if I take a beaker, if I just take a beaker and put some water in it and we consider this is the system. So, the beaker with the water in it is make the system, and everything outside the beaker is what we call surroundings. So, basically when we are doing we are doing a reaction in a round bottom flask, the flask containing the round bottom flask, the reactants and the products are basically our system, and everything else which is not belong to the system we call surroundings. And systems could be of different types. The main three types of system we will talk about is open system, open system where a system can interact or exchange matter and energy with surroundings. So, basically open system can exchange, I should write exchange here, can exchange matter and energy with surroundings. So, the example we talked about the beaker or say a conical flask, if we can draw a conical flask here. And we are taking some reactants here, and this is not tied properly, it is open, then it actually can exchange the matter, the molecules which are in the system, and of course, it can exchange energies with surroundings. So, this is an example of open system. If we consider our own body, myself as a system, then obviously we exchange matter and and energy with surroundings. So, if you consider a human body is a open system, example of a open system. Obviously, second is a closed system. In a closed system, the system can exchange energy with surroundings, but it cannot any matter with surroundings. So, basically if I had this conical flask and we just lead it properly airtight, so that no molecules can go in and out from this system, then this system cannot exchange with any matter with the surroundings, but because it can exchange energy with system and surroundings. So, that would be the example of a closed system. The third system we will talk about is an isolated system. Obviously, is the third category where no exchange of energy and matter is allowed between the system and the surroundings. Obviously, a closed system which or other way it is an isolated system which is obviously has to be a closed system, because it does not allow the matter to go in and out. But obviously, reverse is not true, all closed systems are not isolated systems. So, basically all isolated systems are closed system, but not all closed system are isolated system. And we will mostly in this unit we will mostly deal with the closed system. Once more, closed systems are systems where the system is not allowed to exchange matter with surroundings, but it can exchange energy with surroundings. And a system is separated from the surroundings by what we call walls or boundaries. So, basically we can write a system is separated from surroundings by various kind of walls or you can call boundaries as well. So, what are the different types of boundaries or walls? First type is rigid or non-rigid. non-rigid is nothing but movable boundaries. If I have say a cylinder with a piston, a gas with a piston, now this can be, this boundary if it is not fixed, if piston is not fixed anywhere here, the volume of this gas can change by movement of this piston. So, in this case this piston surface is the boundary between the system and the surroundings, which is movable. So, that case we will call this as a non-rigid boundary or movable boundary. If this is fixed, if I fix it somewhere, so like I can put a screw here in this case, and we can make this piston fixed here. So, that this is now, this has, the piston has now become non-movable, and obviously these boundaries are or walls are fixed. So, they are not movable either. So, in this case the volume of this system cannot be changed, it has a fixed volume. So, in this case the boundary we call this as a rigid boundary. So, if the boundary is movable, by which it can change the volume of the system, then we call this as a non-rigid boundary or wall. And if the boundary between the system and surroundings is not movable, which means that the volume cannot be changed, the system's volume cannot be changed by changing the position of the wall, in that case the boundary or the wall is called a rigid boundary. The second type is called permeable or impermeable. Obviously, if this boundary, as say this piston is porous, which means the gas inside is allowed to move out to the system, or the gas or something from outside can come inside the system through these boundaries, then we call this boundary as permeable boundary. And if the boundary does not allow any exchange of matter between system and the surroundings, then we call impermeable boundary. So, obviously, this is case if it is a system is surrounded by a impermeable boundary, then obviously, it is a closed system, because this does not allow matter to move in or move out from system. Similarly, if it is if the system is surrounded by a permeable wall, then obviously, the system is a open system, because the matter can exchange between system and surroundings. The third type we call, we are talking about these are walls, is adiabatic or non-adiabatic. Non-adiabatic is sometimes called diathermal or diathermic walls as well. Now, in this case, if the boundary between system and surroundings allows exchange of heat between system and surroundings, then we call that is a non-adiabatic or diathermal boundary, which is basically in this case the boundary consists of thermally conductive material, but if the system is surrounded by a boundary which does not allow any heat exchange between the system and surroundings, then we call the boundary or the wall as a adiabatic wall. Adiabatic wall is very difficult to achieve in practice. The most close example we have those flask, thermal flask, where we have actually a double walled boundary with nearly vacuum inside. So, basically that prevent almost prevent exchange of heat between system and surrounding, so that you can keep your drinks or whatever material in the thermal flask at higher temperature or a lower temperature for long time. So, that is the closest example of adiabatic boundary we have. Now, obviously, adiabatic boundary will not allow something to permit the matters to go in out. So, adiabatic boundary will, the system surrounded by adiabatic boundary or walls has to be closed system, and system surrounded by impermeable walls has to be closed system also. If the system is surrounded by permeable boundary, then it is a open system, and if a system is surrounded by all three, like a system which is surrounded by rigid, impermeable and adiabatic walls, then what do we call it? It cannot exchange, because rigid, this by moving the boundary in and out, by changing the volume, we can exchange energy. We can exchange energy either by heat, changing the like exchanging heat between system and surroundings. So, if you are closing the system with rigid and adiabatic, that means there is no exchange of energy possible, and of course, if you are in impermeable boundary, then there is no question of matter being passed. So, in this case, matter and exchange, matter and energy is prohibited for exchange between system and surroundings. As a result, we call this as an isolated system. So, as an isolated system would be surrounded by rigid, impermeable and adiabatic boundaries. So, we talked about system and we talked about walls. Now, how do we describe a system? Now, a system, when you describe a system, you have to specify the values of several properties. Like for example, if I want to describe a system, we have to specify the equilibrium pressure, equilibrium temperature, volume, composition. So, these are the some of the properties, the values of which, the values of which need to be specified or mentioned. Then only we will be able to describe the system, and once we do that, we call that a state of the system. So, the state of the or thermodynamic state of the system is specified by or described by specifying the value of the properties of the system. And as I told at the beginning, that in this case we will be in this unit or in this thermodynamic course we will be only dealing with equilibrium properties. So, when you talk about pressure, temperature, volume, composition, we are talking about the equilibrium pressure, equilibrium value of the pressure and equilibrium value of the temperature, equilibrium volume of the system and so on. So, if we have two system, so I have a water here, a bottle of water in this case which I have say 25 degree centigrade and I have a volume or mass is, I know what is the mass and I know what is the temperature, I know what is the pressure inside. Now, if I have another bottle which has have same amount of water with same amount of volume and temperature is same, pressure is same, then we call that these two are of same thermodynamic state. So, basically a thermodynamic state, if I consider this as a system, then the obviously the bottle outside will be the boundary, and to specify this system or describe the system, I have to tell how much amount of, what is the amount of water in it, what is the temperature, what is the pressure, and obviously if you mention these three, the fourth one, the volume will obviously be linked with the fourth. So, we do not always need to specify all the volumes, because sometimes they are linked with each other. For example, if you know that ideal gas, they are linked with the pressure, volume, temperature and the number of moles are linked with this. So, if you know three of them N, T and V, then you will be able to know the fourth one. So, you do not have to mention all the time all the thermodynamic properties, because sum of the value of the sum of the thermodynamic properties can be obtained from the relations between them, and these are called, the relations between the thermodynamic properties are called equation of states. Now, these states or these value, these properties are called also state variables. What is state variable? What are state variables? For example, the values of pressure, volume, temperature, you do not have to, if you mention what is the value, that is enough. So, we do not have to tell the history, how the pressure is achieved or how the volume is achieved, how the temperature in this case is reached. It does not matter the history of the system, it will only the present value with dictate the system or describe the system. So, these are called state variables. So, if I take again the bottle of water and talk about the pressure inside is 1 atmospheric pressure, temperature is 25 degree centigrade and volume and so and so. So, I do not need to mention that whether the water was obtained from melting ice or water was obtained by condensing the vapor. It does not matter, as long as I mention the present value of the temperature, volume, pressure, then this system is fully described, which means that these are called state variables. So, the value of the state variables do not depends on the history of the system, it depends on the present value only. So, these are called state variables. We have some other classification of variables. One is extensive variables or extensive parameters, another intensive parameters or variables. Now, extensive variables depends on the size of the system, which means if you double the size of the system, the value of the variable will double. For example, the volume, if I increase the size, increase the mass. If I have this water bottle again, if I increase the or double the amount of water keeping the pressure and temperature same, then the volume of the water will be double. So, volume in this case is a extensive quantity or extensive parameter, how do you call, all are equal, and basically the total volume of this bottle can be obtained by summing up the volumes of each part of this bottle. So, the value of any extensive variables can be obtained by summing up the value of that particular variables in all part of the system. On the other hand, intensive variables, they do not, intensive variables do not depend on the size of the system. Generally, the value of intensive variables are obtained at any point of the system. If I want to get a temperature of this bottle of water, then I can measure the temperature on the top, or I can measure the temperature at the bottom. It should get the same value of the temperature. So, it does not matter I have a half bottle of water or I have a full bottle of water, temperature would be same. So, in this case the value of temperature in this case, it does not depend on the size of the system. Now, some systems may contain different phases. What does it call phases? So, if I talk about one term density, what is density? Is the extensive quantity or intensive quantity? Obviously, density of a system will depend on what? Will it depend on the size, or it will depend on, it will not depend on the size of the. So, if I talk about what is the density of water in this bottle, it obviously does not depend on the size. So, density is a intensive variable property. Now, if I add some sugar in it, keep on adding, what will happen? At some point of time the water will get saturated and there will be sugar lying on the bottom of this bottle. So, obviously, the system will have both water and the sugar which is in the bottom, lying on the bottom. So, now if I want to find out density in different parts of this system, then obviously there will be different value. For like in the solution there will be one value, and the sugar which is lying on the bottom of this bottle, which will have different value. So, in some cases, if the system does not have same value for all the intensive variables across the system, then we call that as a heterogeneous system. Obviously, pure water will be homogeneous, because the value of density of all the intensive variables, same across the system. But the example I just given you, where some sugar molecules are lying bottom of the bottle, after the saturation is reached, then you will have different value of density in the solution and the sugar. So, though this example of heterogeneous system, and the solution part and the sugar part will mention a different phase. So, there is one phase which is the solution of sugar in water, and another would be the solid sugar phase. So, that is a heterogeneous system, contains more than one phase, and if the system contains only one phase, basically the value of all the intensive properties are same across the system, then we call it a homogeneous system. So, I just gave you example of two types. One is a heterogeneous system and homogeneous system. So, we know what is the thermodynamic state of a system. Now, if we change, if we say we have a state 1, values are say P 1, T 1, V 1 with some n is the value of number of moles amount of substance, and we change the value of say pressure and temperature P 2 and T 2 and say volume also, and without changing the number of moles. So, if you change, it will be a new state of that system, and how the change is brought about, that is called process. A process by which the state of a or thermodynamic state of a system is changed, and there are many different types of process possible, and I will just try to name few of them. For example, we can talk about isothermal process. Isothermal process where temperature is fixed throughout the process all the time, not that the initial temperature and the final temperature is fixed. Isothermal process is the process where temperature is fixed during entire duration of the process, okay, not that only initial temperature is same as the final temperature. Similarly, isobaric process, in this case pressure is fixed throughout the process. Again, it is not only the initial pressure and final pressure is fixed, the pressure is fixed during entire process. Isochoric process where volume is fixed throughout the process. Now, if there is the process there is a process under happening, the state 1 is getting changed to state 2 without any heat exchange, that means the system is surrounded by a adiabatic wall. So, there is a process going on inside the system, which means the system will, and there will be no heat exchange between system and surroundings. In that case, we call that process as adiabatic process. Adiabatic process are the processes where processes taking place in the systems surrounded by adiabatic wall. Obviously, there are other names like cyclic process where the initial state and the final state of the system is same. So, there are the many other possible names which will come across when required. So, we talked about different processes, what you know what is a process is, and then we talked about isothermal process, isobaric process, isochoric process and adiabatic process. Now, let us come back and talk about the system we discussed earlier. Let us talk about again that cylinder with a containing a gas and a piston. This we consider a frictionless piston, so that when it moves there is no friction associated in the walls. So, there is no energy exchange during the friction of the piston and the system. Now, how many different ways a system can exchange energy with surroundings? Say this is a diathermal wall. So, we can exchange heat, and this is a movable piston. Now, if I place this system in a bath which is slightly higher temperature, then heat will come in, there will be heat exchange between surroundings to system. So, heat will come in, as a result the volume will get expanded. So, there is two type of exchange is possible. One is heat exchange, between system and surroundings, and second one we are talking about the volume change, and we call mechanical exchange. Mechanical exchange is nothing but the exchange of energy between system and surroundings because of the movement of the boundary between system and surroundings. Now, if I consider that this is fixed now, this boundary is fixed, not movable or rigid boundary, and then again we heat it up. In that case, there will be no volume expansion or no volume increase. So, in that case only heat exchange is happening between system and surroundings. In the third case, if I have, say this wall is a adiabatic wall which prevents any exchange between system, any exchange of heat between system and surroundings, and this is movable. So, if I change the pressure, just apply more pressure than inside, then this piston will move in, volume will decrease. So, there will be exchange of mechanical exchange, we call there is a work, the surroundings is working on the system, and if the pressure outside is lower than inside, then the system will move up, the piston will move up, volume will increase, and we call that the system is working on the system, and there is a mechanical energy exchange, mechanical exchange between the system and surroundings. This the work due to the volume change also sometimes called PV work, which is nothing but the mechanical energy exchange as explained here, we call work exchange as well. So, work exchange happen, the energy exchange between system and surroundings, energy exchange between system and surroundings happen as work when the non rigid wall move due to difference in pressure inside and outside the system. Similarly, energy exchange between system and surroundings happen as heat. I am not writing that again, okay, I can write that energy exchange between system and surroundings happens as heat. Earlier it was work, now it is heat when there is a temperature difference between system and surroundings. So, basically we now know that a system and surroundings can exchange energy by two modes. One is work, another is heat. System and surroundings can exchange energy between them either by work. Work comes when the movable boundary moves and the system and surrounding can exchange energy as a heat when there is a temperature difference between system and surroundings. Now, we talk about the energy of the system. We are talking about the energy of systems. Now, what are the different types of energy a system have? Obviously, if I have a macroscopic object which is moving, maybe I'll give you one more example of heat exchange and work exchange before I come to the type of energy. Let me just give you one again I have a piston here, and in this case I have urea, and I am doing a reaction here within this cylinder. So, beginning I have urea, this is urea and oxygen, and I keep this is in a say in a water bath outside, and once the reaction is done, if this is having a movable boundary, then because of you have now more number of the volume of the gases increases, the volume will now increase. Maybe I will draw here. Plus water here, liquid water here, and you have this is placed in a water bath. Now, in this case the system is doing some work on the surroundings because of the volume expansion, plus there will be some energy exchange between the surroundings, which is the water bath here, and if you can measure the temperature before and after the reaction in the surroundings, which might with a very sensitive thermometer, we will see there is a temperature change in the water bath here. Now, if I do the same reaction with a fixed piston, So, there is no volume change is allowed in this case, water then what we will see this case that there is no exchange of energy as a work, but in this case the temperature difference between the system and surroundings or the temperature change you will observe in the surroundings, in this case water will be higher compared to the first case. So, if my drawing is probably is not good here, but anyway what I am trying to say is that I am doing a reaction burning of urea inside a cylinder with a movable piston, and the container is kept in a water bath. Now, if because there is the volume of gas is increasing, if this piston is movable, then the volume of the system will go up, which means there is exchange of energy between system and surroundings as work, and there will be exchange of heat between system and surroundings, and there will be change in temperature in the surroundings here in the water bath. If we do the same reaction in fixed volume where the piston is fixed, then there will be no exchange of work, no exchange of energy as work between system and surroundings. In that case, the difference between the initial and final temperature in the surroundings will be more compared to the last case. Okay. So, basically we now know that there are two ways system and surroundings can exchange energy. One is heat and the other is heat and another is work. Now, what are the different energy in a system? If we just talk about say this pen, this is not moving. So, the macroscopic kinetic energy of this pen is 0, and if we though it is in a height, maybe in a table, so there is some bit of potential energy, gravitational potential energy, but that is also we can neglect. So, you are talking about, and if there is no external field from applied from outside, then there is no potential energy either. So, in this case, if I instead of a pen I am taking a beaker or a conical flask where I want to do a reaction, generally it does not, the beaker or conical flask does not have any macroscopic kinetic energy or potential energy. Then what is the energy a reaction medium, a chemical reaction medium will have? The energy is from the molecules which are present in the system, and that energy is called internal energy. The internal energy is basically the energy due to the molecules present within the system, and what are those energies which are associated with those molecules, I will just explain in a minute. So, as I said, if I just have a conical flask, and we talk about a process from state 1 to state 2. So, and if I tell k is the macroscopic kinetic energy, then del k is 0. Obviously, before and after both kinetic energy is 0. So, k is macroscopic and while changing the state of the system, there is no change in macroscopic kinetic energy. if you do not apply or change the potential from outside, then the macroscopic potential energy V is also 0. So, there is no change in macroscopic quantity of kinetic energy or potential energy. So, what could be the change between say state 1, thermodynamic state 1 to thermodynamic state 2? There could be change in internal energy. If you express internal energy as U, then the change would be del U. So, if I want to find out total energy change of the system for going state 1 to state 2 would be given by del E, total energy, del K is total change in macroscopic kinetic energy, macroscopic potential energy plus del U. And obviously, as we mentioned, the type of system, chemical system we will be dealing with in this unit, or generally we deal with in thermodynamics, these two terms are 0. So, the total change is equal to the total change in internal energy. So, basically now onwards we will be focusing on, when you are talking about the change in total energy of a system, we will be focusing mainly on the change in internal energy, not any other energy. Of course, now the question you will ask, what is the internal energy? So, internal energy U, which is due to the molecular motions plus intermolecular interactions. So, U consists of the translational energy of the molecules. So, molecular translational plus rotational, vibrational, and electronic energies of the molecule, plus relativistic rest mass energy m rest c square of the electrons and the nuclei, plus the potential energy of interaction between the molecules. So, this lecture I will stop here, and in the next lecture, in lecture 2, I will continue from our discussion about internal energy. So, we will just take this slide and then page, and we will continue in the next lecture more about internal energy.